Good morning, everybody. I'm sorry I can't be here with you today. I have a family wedding on the East Coast that I will be attending, but we are going to keep going with physics, and today is a huge day. Today is actually probably the most important day of class of the year because I'm going to give you the 6 equations that will let you predict any and all types of motion, including motion with acceleration. Before we get too deep, I do want to point out 2 things about these equations that are listed on your note sheet. The first thing is that these only work when there is a constant acceleration. We always deal with constant accelerations in this class, but if you are going to extend your study of physics into college, you may have times where you will not have constant accelerations, and I think it's important just to have the disclaimer that these will not work in those situations. Also, we might see problems where there's constant accelerations that act of different values at different times. If you ever have a problem where that occurs, you would need to sort of isolate the different accelerations and solve those problems in parts. The second thing about these equations is the variable d is actually displacement. Now that we're getting a little further into our study of physics, we sort of stop caring about speed and really only care about velocity, and likewise we stop caring about distance and really only care about displacement. I just write d for displacement because it's easier than writing delta x. All right, let's look at these equations. They are right here. You will probably recognize all of these symbols, but I just want to talk you through some of the highlights. First equation, x2 is equal to x1 plus d. Please remember the variable x is position, right? So basically my final position equals my initial position plus my displacement or my change in position. That makes sense. You've probably kind of used this in your head when you've just been sort of logicking where things go. This is a more formal way to write it. Number 2, d is equal to v bar t. Friendly reminder that v bar is average velocity, right? So my displacement is equal to my average velocity times the time that I traveled at that average velocity. Equation number 3, v2 is equal to v1 plus at. This means my final velocity is equal to my initial velocity plus my acceleration times my time. Equation number 4 is the big one. Equation number 4 is a great equation. D is equal to v1t plus 1/2 at squared. Please just remember the t here is squared, and the only thing here that is squared is the t. 1/2 times the acceleration times the time squared is what you need. Number 5, v bar is equal to v1 plus v2 over 2. This is just the definition of an average, and this only works once again when you have a constant acceleration. And then lastly, equation number 6. I love equation number 6. v2 squared is equal to v1 squared plus 2ad. Sometimes people get a little confused with these subscripts denoting the v1 and the v2, my initial and my final velocity, versus the superscripts, aka the squared. These quantities are both squared. I would also encourage you maybe to make a little note on your paper around equation number 6. Equation number 6 is great when you don't have time, right? A lot of these other ones have t terms in there. If you do not have the time for an equation, I would recommend starting with equation number 6. It's probably going to be the one. With these equations, we're going to be solving any and all types of physics problems. These are sort of the classic, like if I start with this velocity and I have this acceleration, like how fast am I going after 5 seconds, or how far do I go? This is sort of the heart of physics and what most people think about when they think about a physics class. When we are solving these problems, it is very important that we are showing our work, and we have these steps to show work right here. You know these, but I really just want to have them in writing, discuss it, and then we are going to solve some problems, and I am going to obviously go through all these steps and show my work in a classroom approved manner, as I always do. Step 1, you're going to list the known and the unknown values. We are then going to write the equation in its untouched symbolic form, exactly the way it appears on the formula sheet, followed by some type of math. You can either plug the numbers in and then do the algebra, whatever you need with the numbers, or you can do the algebra with the symbols. I would highly encourage you to do the algebra with the symbols. I always do the algebra with the symbols, and when we get later on in the year, you're actually going to have to for some types of problems. So I think the earlier that you can get comfortable doing math with symbols, the better. And then lastly, after we have done all of our work, we are going to circle our answer, and we're going to make sure that it has the correct units. All right, so we are going to now solve 2 example problems. I'm going to encourage you, please, to pause the video if you would like to solve them by yourself. I will do everything. Any mark that ends up on my board needs to end up on your note sheet. So please, please, please carefully take notes, carefully write everything down, make sure it is all there. So we are going to dive into example 1. Once again, if you want to do this by yourself, that is totally fine, but please, please, please make sure that all of the work I'm showing, everything that I am putting on the board also ends up on your paper. So we have a Drew driver's ed student who hits the gas and expertly maintains a constant acceleration. They accelerate from rest to 12 meters per second in 4 seconds. And the first thing we want to find is their acceleration. We are going to show work in a classroom approved manner. Step 1 is going to be to define our known and our unknown variables. So if you read that problem, pull out the numbers, hopefully you should figure out the following. Clearly, the time is 4 seconds, that is stated. It says the student accelerates. It says the student accelerates to 12 meters per second, so that would be V2, my final velocity. We also have a V1 in here. V1 is going to be 0 because it says that the student starts from rest. And lastly, because we are looking for acceleration, we can set A equals question mark. So this is step 1. We have listed the known and the unknown variables. We don't have to go crazy. This is all we need. Now we need to basically figure out which equation am I going to solve. So I need to look back at the 6 equations and I need to find an equation that has a V1, a V2, an A, and a T term, nothing more, nothing less. Looking at the equation, that happens to be equation number 3. So step 2 of showing my work, I am going to write equation number 3 in its untouched symbolic form. Like so. Next, I'm going to do math. If you wanted to plug in numbers right here and do algebra for A, that is totally fine. I am always going to do algebra with the symbols, and I would encourage you to do the same. So we could say V2 minus V1 equals AT. We can say A is equal to V2 minus V1 all over T. So I'm going a little fast. Please feel free to pause if you need to. I rearrange the equation, get acceleration by itself. Then I'm going to plug in the numbers. Plug in my numbers, do my math, get to a final answer circled with the appropriate units. That is how I would do part A, showing all of my work in a classroom approved manner. The acceleration is 3 meters per second squared. Moving on to part B, which is how far does the student travel in this time? So I am not going to do step 1 of showing my work again. You don't need to. We've already defined the known and the unknown variables, and you don't need to do that again and again and again. I will, however, write D equals question mark. That's what we're looking for in part B. So now I'm going to look for an equation that has some combos of D's, T's, V1s, V2s, and we also know the acceleration, which I may want to use. The equation I'm going to want to solve in this scenario is going to be equation number 4. D is equal to V1T plus 1/2 AT squared. So I will once again write the equation in its untouched symbolic form, exactly how it appears on the formula sheet. And I want to show you a really cool trick here. Because the student starts from rest, aka V1 is 0, V1 times time, this whole thing just equals 0, so I'm going to just ignore it. So I will cross that out. Then I'm going to rewrite equation number 4. D is equal to 1/2 AT squared. Unlike in part A, I do not need to do algebra here, right? We are looking for D. D is already by itself, so this is honestly much easier than part A. And I can just plug in some numbers, 1/2, 3 meters per second squared. Time is 4 seconds squared. 1648. And we get that the student travels 24 meters while making that acceleration. Part C is what is the student's average velocity. I am actually going to solve this twice using 2 different equations just to show you that they will always work. Please, please, please write down both of these calculations. In part C, we are looking for average velocity, or V bar. And we have 2 equations that will work for us. We could either use equation number 5 or we could use equation number 2. I will start with equation number 2. So, I mean, you know, equation number 2 is just a manipulation of a velocity equation that you have seen before, but this saves you from having to sort of like do this backwards like you had to do in the first test. So I can plug in my numbers, get an average velocity. So v bar is equal to 24 meters divided by 4 seconds, which equals 6 meters per second. So I could do this with equation number 2. I also could do this with equation number 5. And we will get the exact same answer. I wanted to show you this. One, to show you these equations always work, and 2, there is never a prescribed way to get the answer. Any method that uses any combination of these equations will always work, and I would like to encourage you to explore your options, be creative, and solve these problems in unique ways that work for you. Example 2, let's get it. Once again, if you need to pause the video to write stuff down, please do so. That is highly encouraged. So we have Victor and Mikhail both starting at rest, with Mikhail some unknown distance behind Victor. At time 0, they both start accelerating at different rates, and eventually Mikhail catches up to Victor after traveling 40 meters. We want to find a variety of things, starting with the time it took for this meetup to occur. I have already identified my known and unknown variables. They both start at rest, so V1 for both of them is going to be 0. And then I'm just using V's and M's to denote like what's Victor doing versus what Mikhail is doing. In part 1, we are looking for the time. We also know that Mikhail's distance is 40 meters. That's going to matter here very much. So I need an equation that has some D's, some V's, some A's, and some T's. The equation that we're going to want to solve in this scenario is going to be equation number 4 once again. D is equal to V1t plus 1/2 AT squared. Because V1 is 0, I can do the same trick that I did in the other problem. I can get rid of that initial V1t term. So D is just 1/2 AT squared. We are looking for time, so I do need to do algebra to get the t by itself. I'm basically meaning I need to get rid of everything over here to get t by itself. I like to multiply by 2 to get rid of the 1/2. So multiplying by 2 makes 2d equal to AT squared. And then I'm going to divide the a. So we will get t squared is equal to 2d over a, which becomes t is equal to root 2d over a. That is my equation. You'll get more and more comfortable with this. If you wanted to go straight from here to here at a later date, that is totally fine. We then plug in numbers. T is equal to root 2 times 40 meters divided by, I want to use 3. And that will give me 4.85. Took 4.85 seconds for them to meet up. For part B, I drew a little picture just to sort of help frame what is going on, right? We have Victor sort of starting in front of Mikhail, and then once Mikhail has traveled all 40 meters, him and Victor are more or less in the same place, and we want to figure out this distance. How far away are they? We also have the time. That is going to make a difference, so we can use that time from part A here. My strategy for this problem is basically I am going to figure out how far Victor travels in this time, and we already know how far Mikhail traveled in that time. So if we do a little bit of subtraction, we can basically figure out how far away they started from each other. So once again, I will use equation number 4. However, this time I'm going to solve things for Victor, so I just want to really make sure that I'm using that acceleration of 2.1, not the acceleration of 3.4. I can ditch the V1 term. D is equal to 1/2 AT squared. I can plug in some numbers. So we get in the time that it took Mikhail to travel 40 meters, Victor traveled 24.7 meters. So basically we now need to do a little subtraction to figure out how far away they started from each other. So we can basically just say 40 meters minus 24.7 meters, which becomes 15.3 meters. That is going to be how far away they were, right? Victor travels 24.7 meters, while Mikhail travels 40 meters, meaning they must have started 15.3 meters away. Let's do part 3, finish this up. We want to know how fast they are both going when they are meeting up. They are not going to have the same velocity, right? They are traveling different distances in the same amount of time. They have different accelerations, so they are definitely going to be going different speeds. Just for fun, I'm going to solve 2 different equations here. Once again, there's many options. You could solve the same equation twice, but we have a bunch of equations. Let's solve all of them. So first off, I will use equation number 6 for Mikhail, because we know he travels 40 meters. Once again, V1 is 0, so I can get rid of that. So V2 is just equal to root 2AD, which is equal to root 2 Mikhail is 3.4 meters per second squared, 40 meters. We get that Mikhail's velocity is going to be 16.49 meters per second. And now for Victor, let's just use equation number 3. We have the time, so we could have used it. So let's do that for Victor. We get a little V2 is equal to V1 plus AT. Once again, V1 is 0. So we can just say V2 is equal to AT, which is 2.1 meters per second squared, multiplied by the time of 4.85 seconds. That gives me 10. M-I-K-A-L. Label my answers, circle them. That is what we need. All right, awesome. Thank you so much for watching. I hope you enjoyed this rousing physics tutorial on using the 6 equations. Don't forget to hit that subscribe button, give the video a like, click that bell for the notifications. We got a lot of awesome physics class related content coming your way that I know you don't want to miss. In all actuality, we have taken all of these notes. Please show these notes to the substitute. They are going to make sure that you have written everything down and showed your work in a classroom approved manner. When that gets checked off, you may begin working on homework. If you would like to collaborate with groups of 3 to 4 people, that is totally fine. Dive in, see what you can do, and I look forward to seeing you on Tuesday with completed homework.